So this is the continuation of previous video lecture of module 5, and we'll be starting with elasticity. Now elasticity, this term we know, it is the property by which a material returns to its original state after deformation, and generally we get elasticity by plotting the stress strain curve of individual materials. Now it is assumed that the concrete is elastic in nature, that is it will return back to its original position after being loaded at a certain rate. Second, we consider it to be isotropic, that is we consider the properties of the material to be same throughout the cross section. And third, we consider it to be homogeneous, that is every corner will have the same amount of constituent, every part or every portion of the concrete will have same amount of constitution of the materials. But in reality it is not perfectly elastic, it is not isotropic, because properties will vary across the cross section because of the cracks that are there, micro cracks which are produced in the body of the concrete. We also call them as flaws. And third, it is not always homogeneous, because many a times there is segregation of aggregates. Aggregates tend to separate from the paste, cement paste, so we cannot call it as perfectly homogeneous as well. So rheological studies are done on concrete, in which the flow, how the concrete is going to flow in its plastic stage. So it is going to have these two stages, right? Plastic stage, and then it has a hardened stage. So in plastic stage it can flow, and the study of that flow would be called as rheological studies. Also in the hardened state, when it deforms due to certain loading, then the study of that loading would be called as again rheological studies. These rheological studies are very important for concrete, because deformation of concrete is not simple, and it depends on magnitude of loading, rate of loading, and elapsed time after which observation is taken. Magnitude of loading means how big or how heavy of the load that we are putting on the concrete. So definitely the deformation of concrete is going to depend on how much load we are putting on the concrete. Second is the rate of loading. So rate of loading, you should understand that when we perform tests in the laboratory, the rate of loading is gradual. We vary from 0 to a particular load, and then we plot the stress strain curve. But there are times when there are loadings like impact loading. So when the load suddenly rises, or even you can say blast load, because of the blast that takes place at a certain point, because of that the sound waves that hit the concrete, they are very sudden. So such kind of loadings will have higher rate of loading. And the third one is elapsed time, because it is seen that as the time elapses, even under a sustained loading, the concrete behaves differently. There is creep that sets into the concrete, and we'll be learning what creep means in the concrete. And because of that creep, the concrete shows excessive deformation under the same loading. When we plot the stress strain curve of concrete, we are familiar with this curve. From this curve, we need to determine the modulus of elasticity. Now in steel, when we plot the same curve, we get something like this, right? And the initial part is straight. So we just take the slope of this initial part, and then we get the modulus of elasticity in steel. But in concrete, what happens is that straight portion is very small, or it is negligible, and it is almost curved right from the beginning point. So modulus of elasticity is first of all determined by compression testing of cubes, that is by attaching dial gauges and then recording the strains, and or we get it by compression testing of cylinder, or we get it by flexural testing of beam using deflection equations. So like if we are testing for a single point load, then we know that deflection is PL cube upon 48 EI. So the load you will be knowing at which this deflection has occurred, the length of the beam you will be knowing, moment of inertia you will be knowing, so you can find the modulus of elasticity. That is fine. But The modulus of elasticity found by above methods is called as static modulus of elasticity. We have also come across a term called as dynamic modulus of elasticity in the previous lectures, in which the vibrations, due to vibrations, the modulus of elasticity that we obtain is the dynamic modulus of elasticity, whereas this is due to the static loading, as the load does not changes or it does not move, it is at the same position and it is causing the deflection. Modulus of elasticity is strictly upright to the straight part of the curve. However, the stress strain graph for concrete is almost curved right from the origin, and therefore following three methods are used to define modulus of elasticity. So as I told you that in steel it is easier to find the modulus of elasticity because it has a straight line till the elastic point, so we can take the slope. But in this you can see that there is almost no straight line, it's curved from the start, from the beginning itself. So how to find the modulus of elasticity? Now there are three ways of finding modulus of elasticity for concrete. First is initial tangent modulus. So we draw a tangent at the point, initial point, to this curve, and we take slope of this tangent. So this is a tangent drawn from the origin and generally gives accurate modulus of elasticity for lower strength of concretes. Okay. Second is tangent modulus at any other point. So at any point on this curve, if we take a tangent to that point, the slope of that tangent would give you a modulus of elasticity. So this is the tangent drawn at any point. The value of modulus of elasticity will be satisfactory only for stress levels in the vicinity of the point considered. So only for stress levels near this point that modulus of elasticity would be correct, but it won't be true for the entire stress strain curve. So if you want to find modulus of elasticity here, then again you'll have to take a tangent modulus. So it is like that. Okay. And the third one is secant modulus. That is, you have to join from the origin to a specified point on the stress strain curve. Now, if the modulus of elasticity is calculated with reference to the slope of this line, the modulus of elasticity is referred as secant modulus. This is most commonly used modulus of elasticity. Generally, this point will be a point where a particular strain would be specified. So for a particular strain, this point would be chosen, or for a particular stress, that point would be chosen. And generally it is like 85% of the characteristic strength. So at that point we choose this point, and then we can join and find the secant modulus of elasticity. Now it is very interesting to see that the concrete, it comprises of aggregates, it comprises of cement paste, and then it also, if it is a RCC, it will also comprise of steel. For aggregates, the initial part is linear. Even for cement paste, the initial part is linear, but then for concrete, when these two mix, the curve becomes the stress strain curve becomes curved at the start, right? So why is it so? When the aggregate is, for aggregate it is linear, and for cement paste it is linear. Even for steel it would be linear in the beginning. This can happen due to micro cracks that form between the cement and the aggregate. So we had seen the initiation of flaws and micro cracks at the boundary of the transition layer, or at the boundary of the aggregate and the cement paste. Because of those micro cracks, the concrete does not behave linearly in its modulus of elasticity, and it forms a curvature. So yeah, IS 456 has given an empirical formula for short-term static modulus of elasticity, and it is EC is equal to 5000 root FCK. It is given in clause 6.2.3.1. So we are familiar with this equation, and even in previous lectures I had shown this. FCK is the characteristic compressive strength of concrete in megapascal at 28 days. Now, modulus of elasticity, we saw that it is short-term static modulus of elasticity, and then there is something called as long-term modulus of elasticity. And even in this equation, you can see the word short-term is used. So what is this short term and long term? Both are static modulus of elasticity, so it is nothing like dynamic or static. Both are static, but one is short term and other is long term. The short term can be found out by three methods that we just saw: initial tangent modulus and secant modulus. The one that IS 456 gives is the initial tangent modulus. So this formula is for initial tangent modulus and not for other two. Long-term modulus of elasticity will consider two criteria. It will consider creep and it will also consider shrinkage. So this static, we can use static modulus of elasticity. Short-term static modulus of elasticity can be used in the beginning for the design process. But if you are interested in finding the strength of already cast concrete and you want to make some design calculation for already cast building, then you will have to consider the age for which that building was cast, and depending on that you will have to consider the creep and the shrinkage. Creep again we will be learning later on. So at what age that building is currently there, and depending on that we have our long-term modulus of elasticity ECE, which is EC upon 1 plus theta. EC is again this 5000 root FCK, but this additional term 1 plus theta comes into consideration, where theta is creep coefficient, and like for 7 days of loading it is 2.2, 28 days it is 1.6, 1 year it is 1.1. Let us start with the definition of creep. So it can be defined as gradual increase in strain with no significant increase in stress applied for a considerable time, or it can also be defined as the increase in strain under sustained stress. Sustained stress means it is not increasing, it is constant. So creep is influenced by two factors. First is the cement paste gel and the second is the aggregates. That is, depending on size, type and properties of aggregate, the creep will be more or it will be less. So what this exactly means, that increase in strain and under a constant stress, let us see in this stress strain diagram. So for a particular loading, this is a superimposed load for a simply supported structure. The stress strain for a long duration of time would be something like this. As you can see here at this point, as you move further, the strain is increasing but the stress will remain constant. So this generally happens for a loading that is for a significant amount of time. So for a given loading, the stress and strain will increase correspondingly as per the loading. However, for prolonged duration under the same load, there is an increase in strain without increase in stress. So first it will show a normal behavior till this point, but as the load is sustained on the member for a long time, then it will show increase in strain for a constant stress. So this increase in strain without significant increase in stress is called as creep. Now when we talk about the loading, we talk about the working and the ultimate load, and in working load we also include the dead load of this beam as well as the superimposed load. But when we consider creep, we will not consider creep due to dead load. It is only due to the superimposed load. So whatever increase in strain for a constant stress is there due to superimposed load, that will be called as a creep. Now let us understand the phenomena of creep in more detail. So a cement paste gel will have three constituents. First is unhydrated cement grains, second is hydrated products in form of gel, and third is water. Now these hydrated products in the form of gel, they will have gel pores and they will have capillary cavities. So gel is like nothing but it is the mixture of the hydrated cement grains and water, means the one which has reacted with the water, that forming a gel kind of thing, that is called as gel pores. And capillary cavities means those voids which are present in the gel. When we come to water, we have first of all combined water. Combined water is the one which has reacted with those cement grains, so we cannot take that water out. It has reacted chemically, and if we want to take that water out, you have to do some reverse chemical reactions and something like that. So we just have to understand that combined water cannot be taken out from the hydrated products. Second, we have gel water. This gel water is present in the gel pores. So these gel pores are basically filled with the gel water. And third, we have capillary water. Now these capillary cavities, which are basically voids, they may or may not be filled with water. The ones which are filled with water, that water is called as the capillary water. So in water, what we can understand is that combined water cannot be separated, but the gel water which is mixed with the gel pores, that can be taken out, and the capillary water which is there in the voids, that can also be taken out. So when we load a structure, this water can be displaced when the structure is loaded. Okay, and after that, after a certain amount of time, these unhydrated cement grains will again get hydrated as the time passes, because we know that this hydration process takes place forever, or it is basically a very long term process in the concrete, and these unhydrated cement grains, they will get hydrated and they will again go into this stage, where again they will be having gel pores and capillary cavities and everything, right? So what is important here to note is that which type of water can be displaced. Now, knowing that the gel water and the capillary water can be displaced, consider this case when the water is not allowed to expel out. So we have a like tight kind of box thing through which the water cannot expel out. Consider this stage of loading to be one where molecules have taken the initial stress from the load, and they are on the stage of creep. So when this structure is loaded, what it will do is that these molecules of cement grains which are there, they will pass the load, they will dissipate the load amongst themselves, and this water will just get displaced inside. It cannot move out of this structure because we are not allowing the water to expel out. So when we are not allowing the water to expel out, what will happen is the load that has passed onto water, it will just build pressure in the water, and that pressure will again be distributed to other particles. So what is exactly happening when we are not allowing the water to go out of the system is we are building the pressure inside the system when the load is applied, and that pressure is merely being distributed to other particles. So nothing more is happening in this. But consider a case where we can allow the water to move out of the system. So if water is allowed to expel, it facilitates sliding of solid mass over each other. So now see, when a load is applied on this, you saw what happened. And consider that before sliding, this is the length L of the structure. This is the length L of the structure, and after sliding takes place, after this water expels out, now this is the length of the structure. You see what happened? The water expelled out, sliding took place. There was no stress built up in the cement particles, but there was an increase in length. What is strain? Strain is increase in length upon original length. So L dash minus L upon L, this will be called as strain, right? So we got strain, but stress was not there in this. Or stress remained constant because of the sliding part. There was no built up of stress, but the strain happened in this system. Right, so the increase in length here is just a depiction of increased strain without any increase in overburden stress. So this is just a very vague example, or a very simple example to show you how that creep exactly works. Now in theory, we have two theories for creeps. First is macroscopic rheological approach, and the second is microscopic rheological approach. When we consider the macroscopic rheological approach, just see, we have the solid phase and then we have the liquid phase inside a concrete. This solid and liquid phase can be depicted as a spring model. This is called as the rheological spring model. So how this rheological spring model depicts the creep? You can see here that this spring is there, and in between there is a pot in which there is a viscous liquid. So that viscous liquid represents the liquid that is there in the body of the concrete, and this spring, it will represent the solid particles, which actually they just transfer the stress from one body to other body. So this spring is also the doing the same thing, it is transferring stress. Now consider that the liquid which is there, it cannot be dissipated out. So when we apply stress over it, and this stress is translated to this particular through this mechanism, and it tries to displace the liquid from inside. Since it cannot be displaced inside, this entire structure remains static, or it just transfers the stress through these springs and it does nothing. But consider the case when when the water or when the liquid in this can be expelled out. So in that case, what will happen when we apply stress over it? This liquid can be expelled out, so this entire mechanism can come down now, and then this spring which is there, it will also come down. So in such case, we can say that the creep has taken place. The second, that is the microscopic rheological approach. In this, cement gel considered to be anisotropic randomly oriented crystals, and when loaded, the crystals undergo. So here, what this approach considers is that this cement gel which is there, it is a randomly oriented structure, and when it is subjected to stresses, there will be three types of deformation that will happen. First of all, it will be volumetric contraction, that you can see here in this image. You can see that this particular gel molecule is undergoing volumetric contraction. This particular gel molecule is undergoing separation, and this is undergoing pure shear. So there will be three types of the thing that takes place, and after the load is removed, this volumetric contraction that had taken place, it can return back to its original position. But the separation that has taken place of the gel, that is not possible to come back even when the load is removed. And even in this pure shear, only part recovery is possible. So what we can understand from this is that when the load is applied, there will be what contraction, separation and shearing. After loading is removed, there will be only part recovery of your material, and the rest of the material will be permanently deformed, or irrecoverable volume changes will take place on the removal of load. So what it will represent is, even after loading is removed, there is a permanent deformation that has taken place, a permanent volume change that has taken place, but the stress has remained the same. So this is again one of the theory that is given for the creep. So this was it for today's lecture. In the next lecture, we will be learning some more about hardened concrete. Till then, take care. Thank you.